Hello everyone, my name is Saufnay. I'm a PhD candidate and a teaching assistant in the Steel and Composite Structure department at the University of Liège. It's a real pleasure for me to have the opportunity to present my work today. So what I will be talking about is the economic benefit of high-strength steel section for steel structure. The order of the presentation is as follows. So first of all, I'm going to describe the several objectives of the research carried out at the University of Liège. Then I will describe the adopted methodology and show the result for tension and compression member. Finally, I am going to present you two methods in order to help designers choosing the most suitable steel grades, and some results of an economic study performed on the cost ratio parameter in order to see how a change of this parameter can impact the economic benefit in using an high-strength steel grade. And I will give you finally some conclusion and perspective works. The various objectives of this research are reported on this slide. So the first one is to identify the interest field in which high-strength steel H-shape and Y-shape section present an economic benefit. The second one is to develop tools in order to ease the comparison between steel grades. The third one is to understand the key failures which limits the benefit of such grades. To establish methods for designers and manufacturers in order to help them choosing the most appropriate steel grades. To compare existing steel grades or even future emerging steel grades because some grades are not existing yet in the European steel market. And to implement the methodology for various member typologies. As a reminder, the main goal of this study is to evaluate the economic benefit in using an high-strength steel instead of a regular steel for structural members. In this presentation, the S500 will be considered as the high-strength steel grade, and the S355 will be considered as the regular steel grade. The general structure of the developed algorithm is the following. So optimum designs for both the steel grades are performed in parallel. Once it's done, a cost comparison of the two designs is performed, and a field of economic benefit can be determined. The optimum design is based on the new version of Eurocode 3 Part 1.1, which covers steel grades up to S700. Load and length range based on common building values, thanks to an ArcelorMittal project which is called C-Shallow. And the fundamental interest condition is expressed as the rate ratio between the regular steel grade and the high-strength steel grade has to be bigger than the relative cost of the high-strength steel grade in order to present an interest in using this particular steel grade. The various member typologies which were covered in this research are the axially loaded columns with or without any axial bending, the secondary beams which are subjected to an uniform loading, and the primary beams which are subjected to a point loading. Only the columns in tension and pure compression will be described in this research. However, if you are interested, further results can be found in my master thesis online. The relative costs considered in this research are the material cost ratio values proposed by Professor Johansson in 2005 for steel EV plates and strips. The main reason explaining this choice are the fact that hot roll sections higher than S460 are not yet produced in the European steel market, and it seems that this curve is still the reference in the current literature. However, there is ongoing research at the University of Liège concerning the establishment of a more accurate relative cost curve for various. Now let's explain the results for tension members. The main assumptions are we consider only HEA range. The HEA range. The two compare steel grades are the S500 and the S355, and all the designs are performed considering ULS condition. The first chart is the number of gap profile. The number of gap profile can be defined as the number of profile which separates two optimum design profile. As an example, if we get the HEA 140 for the regular steel and the HEA 120 for the high strength steel, there is one gap profile. But to know if there is an interest or not, you need to know if the weight ratio is below or higher than the relative cost. So we plot the weight ratio evolution for the HEA profile range, and as you can see, it is not a constant, so sometimes the weight ratio is below, sometimes it's higher than the relative cost. And the final result is here. So as you can see, there is two areas of non-interest. The first no interest area is an area in which there is no gap profile. So it can be explained by the fact that the HEA 100, the first profile of the range, is sufficient for both steel grades. And the second no interest area, which is marked with the little star, is an area in which there is one gap profile, but the corresponding ratio is below than the relative cost, so there is no interest. As a conclusion, there is no interest if the optimum regular steel profile is HEA 100, and the interest anywhere else in the domain is dependent on the fundamental relation expressed previously. Now let's explain the results for compression member in the same way as for tension members. The main assumptions are we consider only HEA columns with spin support condition. We consider buckling about major axis only, and the same steel grades as for tension members. The results are reported here, and they can be explained thanks to the number of gap profile and the weight ratio evolution. Once again, so as you can see, the areas 4, 8, 9, and 10 are no interest in the above pictures, and it can be explained by the fact that these areas are areas of one gap profile and the corresponding weight ratio are below the relative cost. So there is no interest. And the main conclusion of this second results is the fact that the presence of instabilities, flexural buckling here, considerably limits the economic benefit in using higher steel grades. And it can be explained by representing the European buckling curve for one given profile. As you can see, the higher the slenderness, the same the resistance, and so the less the economic benefit in using the S500 high steel grade. Now I'm going to propose some methods in order to help designers in choosing the most appropriate steel grades. The first method is a graphical or numerical method in which we can know directly the optimum profile for a given steel grade. For example, if we consider a 4-meter column subjected to a compressive load of 1,500 kilonewton, the optimum profiles are HEA 200 and HEA 180 for both steel grades. So there is one gap profile and the weight ratio is equal to 1.19, which has to be bigger than the relative cost of the S500 steel grade in order to present an interest in using this particular grade. So the method 1 consists in the direct determination of the optimum profiles graphically or numerically. The second method proposed for practice is a method in which we represent directly the weight ratio between the two optimum profiles. But the main drawback of this method is the fact that we don't know at the end which is the optimum profile of the most relevant steel grade. However, this chart is particularly useful in order to quantify the impact of change in the relative cost of the high-strength steel. So the method 2 consists in the direct determination of the weight ratio, by contrast with the first method, which gives directly the optimum profile. Now let's finish the presentation with the results of the economic study. So all the developed routines can take as argument any cost ratio curve. So we perform some sensitivity studies to see how a change of the cost ratio is affecting the obtained results. And the results are reported for tension members and compression member on this slide. So as you can see, we can plot the evolution of the percentage of economic benefit in the whole domain, depending on the relative cost. These charts can be very useful for a manufacturer to see how to fix their relative cost. The conclusion of this research are a methodology to compare a solution with different steel grades has been established in this research. Routines of optimization have been developed. A graphical representation of the obtained result is proposed. Some methods are proposed to help practitioners in choosing the most appropriate steel grades. Needs for further developments are identified, and some perspectives. So a publication is currently under review in a journal on this research, and further result can also be found in my master thesis online. Establishment of more accurate relative cost and improvement of the developed algorithm and tools are planned to be performed at the University of Liège, and also an adaptation of the tools for other steel sections like hollow section or welded I-beams. Thank you for watching.